Hi and welcome back. We're discussing the general convergence theorem for stationary iterative methods. Now this is what this theorem says. This iterative process for the stationary method will converge for any initial x0, so no matter what sort of initial guess we choose, if and only if the spectral radius of G is smaller than 1. Now to prove it, we have to split this into two parts. We have to look at the if and the only if part. Now this is a tricky theorem because we really have to understand what if and only if mean. Now the if part of this condition is what we call the sufficiency condition. It basically states that if the spectral radius is smaller than 1, we don't need to be concerned. No matter what initial guess x0 we take, we will always converge. The only if part just tells us that if we do not have the spectral radius smaller than 1, then there will always be initial guesses x0 for which the iteration process does not work. Now sometimes we can understand for which initial guesses we may be in trouble, but other times we just can't, and therefore there is a risk involved. How would we prove if? So for the if statement, we assume that the spectral radius of G is smaller than 1, and we want to show that no matter what initial guess we have, we'll always converge. Now working with the spectral radius, which is an eigenvalue of the matrix, is not always easy because eigenvalues are very complex functions of matrices. But you probably remember that this iteration that we're interested in, mxk plus 1 is nxk plus b, converges if we can find some norm for this matrix G, for which the norm is smaller than 1. Now the matrix G, again, is the amplification matrix of this iteration process, and that's M inverse times n. So now the idea is, for this if proof, that we take this condition, or this assumption, that the spectral radius of G is smaller than 1, and from this we construct some norm for which we can show that the norm of G is smaller than 1, and then we have sufficiency. Constructing this norm is really clever, and we're going to use two things for this. The first one is that the norm that we'll be using is actually a so-called matrix-induced norm like this. A norm like this with the subscript S is simply given by the one norm of this matrix S, G, S inverse. And here S is some non-singular matrix. Now you can show that this is truly a norm, so it satisfies all the properties of norms that we usually assume. So that's the first observation, the first idea. The second thing that we're going to be using is a really important theorem in matrix computations called the Shores Theorem. And actually it's one of my favorite theorems of all times because it's extremely useful in proving concepts, and we'll see that here too. Now what the Shores Theorem says is that any matrix, so also G, can be expressed in this form here as P inverse, where P is some non-singular matrix, times an upper triangular matrix, which we split in two parts, the diagonal and the strictly upper triangular part, we call them D plus U, times P itself. And the beauty of the Shores theorem is that this is true for any matrix, but also D, this diagonal matrix, has all the eigenvalues of G on its diagonal. And this comes directly from similarity between G and D plus U. Now, because all the eigenvalues of the matrix G are on the diagonal of D, it immediately means that the one norm of D itself is equal to the spectral radius of G, and we'll be using that in the proof. Now we take that expression that we get from Shores' theorem and just write it a little bit differently. We move all the p's over to the left-hand side, and we get PG, P inverse, is D plus U. Now comes a tricky part, which is really creative. We construct another matrix T, which is a diagonal matrix, and on this diagonal is on every element 1 divided by T to some power. The first element is just T itself, the second element is T squared, then is T cubed, and so on, all the way down to T to the power n. How do you come up with something like this? Well, it's a lot of playing. So people played and found that this works. So we pre-multiply the expression that we had earlier by T, and we post-multiply by T inverse. And on the right-hand side, we get t dt inverse, but that's just d. You check that for yourself. And the second term that we have is t ut inverse. Now when you take t and t inverse and just plug it in and see what sort of expression you get, you will see you get a strictly upper triangular matrix like this. Now remember that the inverse of a diagonal matrix is again a diagonal matrix, and all the elements along its diagonal are just a reciprocal of the original matrix. So you can plug that in and find this expression for yourself. And what is interesting is that all the elements here that are non-zero are the original elements of U multiplied by a power of t, but these powers are all positive. Now what does this really mean? It means that we can drive all these elements down to very small numbers, in fact as small as we like, just by choosing a small enough t. Now what this means in terms of norms, that if we want to get a one norm of this matrix that is really tiny, all we have to do is choose the appropriate t. In other words, for any epsilon bigger than 0, we can choose a t such that the one norm of this matrix here is smaller than epsilon. Now remember what we're trying to do. We were trying to construct a norm, which we call this S norm, like this, right? Such that when the spectral radius of G is smaller than 1, this norm is also smaller than 1. That would be the sufficiency condition. Now what we're going to do is take S equal to Tp. That's the trick. So Tp, G, P inverse, T inverse, the matrix we've just been working with, is really nothing but SG S inverse. And that was exactly that matrix that we had here in this equivalency for the S norm. Now, SGS inverse, as we just saw, is diagonal t plus TUT inverse. And we know also that the one norm of D is equal to the spectral radius of G. And now we're ready to get the final result. So the S norm of G is equal to the one norm of this matrix here. We know now, because we can use the triangle inequality for the norms, that it is bounded from above by the one norm of D plus the one norm of this matrix here. And this one is the spectral radius of G, so that's what we have here. And this one, we know how to bound by any little number epsilon. Now suppose that rho G is smaller than 1. That was given to us. So there is a slight difference between 1 and rho G. Maybe big difference, maybe really, really tiny difference. But no matter what, we can always choose epsilon, even smaller than the difference, to ensure that GS is also smaller than 1. That's the trick. Now this may seem very contrived and convoluted, but sometimes proofs are like this. But what it shows us is that the condition, spectral radius of G is smaller than 1, is sufficient for convergence. Now we need to do the other side of this proof, and that is the only if part. Now remember that we wanted to show in this part of the proof that if the spectral radius is not smaller than 1, then there is always initial guess x0 for which we are in trouble. So how do we construct such an initial guess? Now in the construction, we can only play with the stuff that we know. And what do we know? We know that the spectral radius is bigger or equal to 1, right? It's not smaller than 1. And we know that there is some eigenvalue equal in absolute value to the spectral radius. So in other words, we have this expression for that eigenvalue lambda and some eigenvector which we call z. Here's the trick. Assume that the initial guess is now chosen such that the initial error, which is x0 minus x, is in this direction of the eigenvector. So x0 minus x, E0, is equal to z. Now again, we don't know what z really is, so this is just a theoretical argument. But suppose that we were very unfortunate and we just choose our x0 such that the initial error points in the direction of the eigenvector corresponding to the spectral radius. What happens then? The error ek at iteration step k is given by g to the power k times the initial error E0. Now the initial error E0 was in the direction of this eigenvector. So if we plug this in, we find that ek is equal to g to the power k times z. But gz is equal to lambda z, where lambda is the spectral radius. So if we apply g k times, in fact what we do is applying lambda k times to z. But because lambda in absolute value is equal to the spectral radius, and the spectral radius in this case is bigger than 1, lambda to the power k just blows up. And so that means that the error, ek, blows up. And we're in trouble. So this concludes the proof for the general convergence theorem. Hope you enjoyed it.